Welcome, everyone. My name is Charlie Bender, and this is the 8th webinar from the Decarbonization Subcommittee. We really appreciate everyone coming this holiday week here in the United States. We have a great hour ahead of us. There's a couple of things that AIST would like to cover before we get to our presenters and moderators. For this webinar, we have disabled each of your attendee audios, and we encourage that questions be sent through the software in the Q&A button. Our hosts and our moderators will determine which questions are presented to the presenter live. The balance of the questions will be answered after the webinar is completed by the presenter. This session is being recorded and will be available for on-demand replay at the AIST website, and photos and recording of presentations are prohibited. Should you have technical difficulties during the webinar, please email training@aist.org. AIST has an antitrust guideline. Please do not participate in price fixing. We also have an anti-harassment policy where we encourage each of our presentations and meetings to be comfortable for each attendee. Again, if you have questions there in the audience, please submit them through the Q&A button of this Zoom software. And if you have technical difficulties, send a request for help to training@aist.org. This line of decarbonization webinars has been a string of information that's been available since way back during the pandemic. And today we have our moderators, both Kyle Vanover and Michelle Vachon, who will then present our individual presenters and move into the presentation. Let me first tell you, Kyle has been enjoying close to 15 years at Steel Dynamics as a metallurgist, and he's earned his master's degree from Purdue University and worked in various departments, including the electric arc furnaces, ladle metallurgy, furnace, caster, and hot rolling mill. He has also dabbled with his technical expertise and analytical skills and creative problem-solving abilities, and is a world-renowned grill master. Our other moderator, Michelle Vachon, is a U.S. Steel, Big River Steel employee, as the environmental manager, and in 2023 became the first divisional manager of sustainability for both Big River Steel in Big River Steel 1 and 2. Her current role includes responsibility for the operational side of Big River Steel's sustainability program and responsible steel site and product certification programs, such as focus on environmental, social, and governance issues. She also represents Big River Steel on the U.S. Steel Sustainability Leadership Steering Team and the U.S. Steel Tactical Greenhouse Gas Reduction Task Force. Prior to being named environmental manager, Vachon consulted for Big River Steel's chief compliance officer from 2014 to 2016, but also for academic institutions, the private manufacturing and nonprofit sector, with focus on brownfield remediation. Michelle earned her bachelor's degree at University of Michigan in Dearborn and majored in environmental studies. She also earned 2 Masters of Science degrees in environmental science and bioregional planning and sustainable communities from the University of Idaho. At this point, I'd like to turn the presentation over, and I will ask our next presentation to start sharing the screen. That would be Jeremy Jones. Michelle, can you tell us a little bit about Jeremy? I'm sorry, Kyle, can you tell us a little bit about Jeremy's background?
Yeah, and it's an honor to do, and I can't even talk, sorry. It's an honor to introduce Jeremy. Since I started in the steel industry, I can say I went to the very first AISTs when I started 15 years ago. and got to meet Jeremy back when I knew absolute nothing about steelmaking. And it's been a pleasure to get to know him and learn from him over the years. So now it's an honor to get to introduce him for his presentation today. Jeremy was born in Tonebridge, England in 1961, immigrated to Canada in 1966. Jeremy grew up in Ottawa, Canada, attended Queen's University, Kingston, Canada, earning his Bachelor's of Science in Chemical Engineering in 1983, followed by a Master's of Science in Chemical Engineering in a glorious year of my birth, 1985. Good job on that, Jeremy. That was a great year. Jeremy is currently a founding partner and president of Continuous Improvement Experts CIX. Previously, he held senior positions at Transfield Services, Tenova, Nopro Corporation, Mutual Corporation of Florida Steel, and Hatch Associates. Sorry if I butchered any names there. Jeremy is frequently invited as a keynote speaker instructor for international steel conferences. He is primary author, EAF Steelmaking chapter for Updated Steelmaking Volume, the Steelmaking Shaping and Treating of Steel, a frequent contributor to AIST conferences, frequent session chair at annual convention, and author of over 100 technical papers and articles. In May 2023, Jeremy was an honorary member of the American Institute of Mining, Metallurgical, and Petroleum Engineers for his commitment to the advancement and education related to international electric steelmaking. Jeremy is a distinguished member of the AIST and a recipient of the John Bell Award for advancing EAF technologies. Jeremy is also a fellow of the International Iron Metallics Association. Jeremy has carried out assignments for clients in over 100 countries. He is the past chairman of the AIST EAF Committee and the past chairman of the World Steel EAF Technology Committee. Jeremy also chaired Continuing Education Committee, the Energy and Environment Committee, and Advanced Technology Committee at ISS, a predecessor to AIST. Jeremy is one of the original instructors of the AIST EAF training seminar, which recently completed its 28th year. Jeremy's steelmaking experience spans direct reduction, smelting reduction, EAF steelmaking, blast furnace operations, BOF operations, ladle metallurgy, vacuum treatment, and casting operations for all grades of steel. Previous assignments have spanned the fields of project management, project negotiations, process engineering, process control and engineering, process simulation and optimization, environmental engineering, industrial engineering, and management consulting. So it's a great honor to get to introduce Jeremy. Thank you.
Thanks, Kyle. So the title of my presentation this morning is The Challenges of DRI Utilization as a Decarbonization Lever for the Steel Industry. And I'm presenting on behalf of CIX, my company, and IIMA, the International Iron Metallics Association, where I'm a technical advisor. And this is just some background on IIMA, but basically the members include almost all of the merchant producers of pig iron, DRI and HBI worldwide, as well as the iron ore producers, the technology suppliers, and others. And then just the standard sort of disclaimer, and we'll move on. So when we look at ore-based metallics, the historical perspective is that we've used ore-based metallics in the EAF for many years, especially here in North America, because we actually started to utilize these materials as we moved into higher and higher quality products in the EAF. And in that respect, North America has led the way. North America was the first region that produced high quality flat products from the EAF. Also in the early days, areas that lacked sufficient scrap to support EAF operations turned to DRI as a source of metallics. Perfect example of that is the Middle East, but also some regions in South America. Areas that have cheap and plentiful natural gas, it was sort of a natural fit. And then as we evolved, as I said, into the higher quality products and the need for better consistency in the operations, we began to use more and more ore-based metallics, and this was coupled with increased use of oxygen in the EAF. So essentially, we have an insufficient supply of prompt scrap to support some of these operations producing flat products. So this necessitated the utilization of DRI, HBI, and pig iron. And then this continued to evolve. And we've reached the point now where ore-based metallics are actually sort of a key enabler for scrap circularity, because as we have rising residual levels in our scrap, we have to find a way to dilute those. We haven't developed any method to remove residuals. So until we do, then dilution is the solution. When we look at advances in EAF technology, further decarbonization of the EAF is heavily dependent on renewable energy, but also on higher quality raw materials. And this is an area that's frequently ignored. Though we have seen a few companies in the US recently embark on programs to produce and generate higher quality scrap to charge to the EAF. In order to get greater renewable energy available, we really need to upgrade the electrical grid. We aren't really situated where we could just sort of flip a switch and transition to all renewable energy in North America right now. We need more efficient power storage technologies and more efficient renewable energy technologies. And we've seen advances with things like the solar cells. Some of the recent advances have doubled the efficiency from around 20% to almost 40%. And those are the kinds of things that we need to see. As a result, hydrogen-based processes are unlikely to be implemented before about 2035, except in regions that already have a very low carbon footprint energy available. So look at Scandinavia and Canada, where there's a lot of hydroelectric. Also in Canada, you have a CANDU, which is a nuclear technology. So those would allow you to produce green hydrogen. But most other parts of the world, it's really grossly uneconomic right now to try to produce green energy, green hydrogen, and the amount of energy that's required is enormous. As I mentioned, we need to understand how scrap fits into the overall picture, because the future is a balance between scrap and ore-based metallics. So if you look at scrap as a decarbonization level, 100% scrap operations utilizing EAFs already have a fairly low CO2 footprint compared to integrated plants. But that's not saying that they don't need to do anything. The footprint can be lowered even more through improvements in efficiency and improving iron yield, as well as removing extraneous material from the scrap before it's recycled. So we really need to understand the properties of the scrap, its value and use. And what we're fighting is that we are seeing increasing levels of scrap residuals, and we need to find a way to slow that down. So when we look at the challenges for scrap, rising residual levels is probably the biggest one. But then a close second is the dirt, gangue, silicon content of scrap. This contributes to the amount of fluxes that are required and has a huge impact on iron yield in the EAF. That's something that I'll dig into in more detail a little bit later. The non-metallics content of scrap, as one of my friends said, we need to stop using the EAF as an incinerator. So we need to remove what we want to put in the furnace is the FE bearing material. Anything else really contributes to either additional waste products, byproducts, or contributes to environmental issues in the operation. We have a lack of definition of scrap characteristics. We tried to address this and have actually defined a global sort of matrix of scrap equivalencies, but there's still work to be done there. The lack of good value and use definition, and again, we've tried to address this within CIX with some of the tools that we've developed. And more importantly now, scrap availability in close proximity to the steel plant, because if you're transporting scrap great distances, there's a carbon footprint associated with that. So here in green, you see the things that we already have a pretty good handle on. Still need a little bit of work, but you see the two that we haven't resolved yet. So when we look at projections of scrap availability, this is data that's generated by World Steel. And you can see that post sort of 2025 in the developed world, the EU, North America, and Japan, scrap availability is pretty flat. The areas where we see a huge increase are in China, the rest of Asia, and then the rest of the world, and especially sort of post about 2030, 2035. Now, that being said, and I hear this argument a lot, oh, there's plenty of scrap available, it's not an issue, but is it the right scrap? And so what we see is that the projections for generation of home scrap fairly flat going out into the future. Prompt scrap, a slight increase as we start to get higher grade products and manufacturing growing in the rest of the world. But what we see is that the obsolete scrap supply increases enormously. And the problem is that this is where we're seeing the steady rise in residual content, which makes it more and more difficult to utilize that material. So we have to come up with solutions, otherwise we'll be landfilling obsolete scrap. So when we look at things like the copper levels, and on average, essentially the average copper residual worldwide right now is probably in the range of 0.25 to 0.3 weight percent. So what that means is, as depending on the product that we're trying to produce with that scrap, the amount of ore-based metallics that we have to add increases. So if the scrap hits 0.5 weight percent copper, which is what the projections are saying we will reach by about 2050, then to produce a 0.1 copper product, you'd have to use 80% ore-based metallics that have essentially zero residuals, and you'd only be able to use 20% of this material. So you can see that by 2050, even if we're producing products like rebar, we might still have to use a portion of ore-based metallics in order to meet our desired chemistries. So in North America, the short-term solution has been dilution. And so we are probably one of the largest users of ore-based metallics in the EAF. And we use those to dilute the residuals. Without the ore-based metallics, a significant amount of obsolete scrap will reach a point where it can't be recycled at all. And the reality is that the availability of prime scrap is shrinking in many of the mature economies, because manufacturers always want to become more and more efficient. And so they're trying to generate lower and lower quantities of scrap. So obviously the amount that can be recycled back to the steelmaker is shrinking. At the same time, some automakers are calling for higher quality flat products made with without some ore-based metallics because of the carbon content and the CO2 footprint associated with them. So this is a bit of a dilemma. But what we have seen is that due to the scarcity of pig iron that came about because of the Ukraine conflict, in North America, several steel makers reacted to this by starting to upgrade scrap quality. Other considerations for the use of ore-based metallics, well, it greatly aids with the consistency of EAF operations, hitting the same sort of melting chemistry. It's very effective for pacing operations in the steel plant. It allows you to utilize more medium and lower grade scrap, helps to close the loop on the circular economy, and greater steelmaking capacity moving towards EAF. So we still see a need for the ore-based metallics. So as a result, DRI and HBI are seen as a major sort of pathway to the decarbonization of steel production. So if we look at some of the projections, these are some of the figures that are being put in various publications. I'm not going to spend a lot of time on these. The slides will be available afterwards, but essentially you see that the plan is to move to EAFs utilizing DRI, eventually with hydrogen, to achieve a very, very low CO2 footprint in the future. And again, just some additional figures on what various groups are projecting out to 2050 and even as far as 2070. The hydrogen-based DRI, so this involves some changes, some adjustments to the operation. This particular slide shows some figures from Midrex. The big issue is that you have to have the hydrogen available. So it's not so much a technological issue to transition to hydrogen-based DRI. It's more of a question of the availability of the hydrogen and the fact that it takes a huge amount of power to produce this level of hydrogen that's required through electrolysis, which is the green sort of approach to producing it. Okay, won't spend a lot of time on that. One of the more concerning factors is the availability of DR grade iron ore. So typically most of the DRI is projected to be used in the EAF. And so ideally we want a very, very high iron content in the material that we have to produce the pellets. We want the acid gangue content to be as low as possible. Okay, and this impacts the more silicon alumina you have in your pellets, The problem is that you typically use almost 1.5 tons of pellets to produce 1 ton of DRI or HBI. So what happens is if you had 2% silica in the incoming pellets, you would have 3% silica in the product. And then this silica and alumina, when the DRI melts in the furnace, it will report to the slag, and you have to offset these acid slag components with basic slag components, lime, dole lime. And fluxes, basic fluxes have a very high CO2 footprint. In addition, this results in much more energy requirements for the slag. It results in higher yield losses. So this has the largest single sort of impact on EAF operations. And really, you can think of gangue as being the same thing as dirt in scrap. And likewise, when we process scrap, we want to try to remove as much of the dirt in order to eliminate the silica and alumina so that it doesn't come into the furnace. The phosphorus, typically we want this to be as low as possible. Again, it's going to get concentrated when we produce our DRI. So when we look at various scenarios, and this is a slide from Chris Barrington at IIMA, and it looks at various projections and shows the amount of DR grade iron ore that's going to be required by 2050. And you can see that it's either triple or quadrupled, depending on the projection that you look at. Chris does a survey every 6 months and actually looks at DR grade iron ore that will be coming online. And when you look at that, even out to 2033, based on the projects that are currently have been announced, we find that we've got a shortfall of about 36 million tons a year of DR grade pellets just by 2033. And so again, if we look at this projection out and knowing that we need 1.45 tons of pellets per ton of DRI, you can see the impact here, how much these new projects are going to increase the demand for these pellets. Now, some people have started to look at developing a process flow sheet whereby you use lower grade pellets in a direct reduction process, followed by hot feed to a melting furnace, which does a very small amount of smelting. And essentially they produce pig iron in this furnace so that they can separate out the gangue into the slag and then use that pig iron hot metal downstream in the BOF. So essentially for some integrated plants, they would maintain the same process flow sheet and just replace the blast furnace, coke oven blast furnace, with a DR shaft and one of these smelting furnaces. When we look at the overall energy efficiency, that can be an issue. Likewise, the capital cost. These tend to be fairly large furnaces. This is a representation from Prime Metals. Just gives you an idea of what we're looking at. And again, it's a new technology for us to have to become familiar with. But there's a projection that by 2033, the demand for the pellets could be reduced, but we still have a significant shortfall that we see here. So let's talk about some of these quality concerns. Well, what we've seen worldwide over the last 15 to 20 years is a steady increase in the phosphorus level in blast furnace pellets. And that's because we tend to mine out the best quality early in the life of a deposit. And now we're getting into blending in other ore that, while its properties are quite good, has higher phosphorus levels. So both acid gangue and phosphorus increase basic flux requirements, increase energy demand, extend your power on time, result in higher yield losses, and result in a higher CO2 footprint per ton of steel. So most EAFs utilizing ore-based metallics with high acid gangue content tend to operate at low slag basicity, typically a B3 of 1.5 to 1.7, in order to reduce the slag volume and the associated impact of the iron losses. And of course, it depends how much of these OBMs you're using in the charge. So what we see is that a lot of existing EAF operations, even those producing flat products, might use anywhere from 10 to 40% OBMs, depending on the grade that's being made. And what we see is that the integrated plants that are looking to transition are all planning on using about 90% OBMs in the furnace charge. So the impact on them is much higher. So the impact of things like gangue, the impact of phosphorus will be much higher on these integrated operations that are transitioning because of the quantity that they're utilizing. Just to give you an idea of what the impact is of an additional 1% gangue or 1% dirt in the scrap, that this is just a summary that we generated within CIX for a 1 million ton a year plant. And what we found is that the cost is about $11 per ton. And the impact on the CO2 footprint is an additional 43 kilos per ton of steel produced. So dirt content and gangue content are really, really important. Now, when it comes to phosphorus, phosphorus removal in the EAF requires high slag basicity, but also requires higher FeO levels in the slag and a low bath temperature in order to promote the driving force to push the phosphorus from the steel into the slag. So if the OBMs have high acid gangue and high phosphorus, the impact gets greatly amplified because you can no longer operate at a low basicity. Now you're going to have to operate at maybe a B3 around 2, maybe 2.5 or even 3, depending on how extreme the situation is. So this can have a significant impact on the amount of flux you have to add and the iron yield losses. So potentially rising phosphorus levels in DR grade pellets have the potential to be a much bigger issue than even acid gangue. And this could have a huge economic impact. So this is something we have to pay attention to. So when we look at some of the tools that we have available to understand our raw materials, internally at CIX, we developed a program that allows comparison of different materials. This program gets tuned to particular furnace operations currently being running at Big River Steel. In fact, we developed this initially at Big River, and they use it to help design charge mixes, but also to plan out their scrap buy each month. And then couple that to a carbon footprint model. And again, this was a model initially that we developed to aid Big River Steel in getting certified under the Responsible Steel Program. So we really have to drive towards cleaner raw material input to steelmaking, and by that I mean lower residual, but also lower dirt or gang content. Okay, the ore quality and availability is going to be very critical to the rate at which DRI and HBI production expands. A much better understanding of raw material value and use and how best to use iron-bearing materials in the EAF is needed. But DRI and HBI are definitely very integral to the circularity of steel scrap and enable higher rates of recycle to be achieved. What we need to do is find the correct balance of OBMs and scrap for the steel products that we're producing. So far, I think in North America, we've done a pretty good job of that. Segregation of higher quality scrap can help to lower the demand for OBMs. And if we can clean up our scrap, if we can reduce the amount of free copper that comes along in our scrap, then we reduce the demand for the OBMs. So that's sort of a sustainability thing and also circularity. So upgrading scrap quality is really integral to sustainability and helping to reduce the carbon footprint. So we need to take a much more multifaceted approach to develop longer-term metallic strategies. If you need more information, you can get it from the IIMA website, or you can contact me, or I can put you in touch with other people if I feel that they have a better answer to your questions. So hopefully that gives you a quick sort of overview of some of the challenges, and happy to entertain any questions.
Excellent, Jeremy. Thank you so much for your presentation. We do have a host of questions lined up in the Q&A, and we'd like to give everyone, as your last screen showed, your contact information. I'll put that up now. And each question will be answered whether live or afterwards. Our presenters will get a complete list of these presentations.
All right, Jeremy, there seems to be a lot of questions about hydrogen-based DRI versus natural gas-based DRI from like a cost standpoint, transportation of hydrogen, and availability of hydrogen. I know you kind of said you weren't going to expand on that much, but there's been multiple questions kind of in that area.
Sure. So the first issue is even having the energy that's required to support a 2 million ton a year DR plant. And so if you had a solar field that was providing the energy to an electrolysis unit to then generate the hydrogen that would go into the DR plant, that solar field would greatly eclipse the area of the DR plant itself. So that's definitely a challenge. If you choose to do it with just conventional fossil fuel generated power, it definitely becomes an economic issue. So the best potential for projects like this are in areas that have a lot of hydroelectric power, that already have a very low CO2 footprint energy available. But again, if you start thinking about, okay, if you need 32 million ton a year plants, if you look at how much energy that is, it's absolutely enormous, and it's just not available right now. I mean, if we look at a lot of parts of the world, they're already stretched with just providing energy to support the infrastructure they already have. So it's something that's going to take time. So first the renewable energy has to develop and evolve, and then the hydrogen will come in afterwards, I think. So it's a very tough road for hydrogen. Like I remember 2 years ago, I spoke at a conference and said, well, that there were a lot of people there who thought that the first hydrogen-based plant was going to be built the following year. Well, I said, okay, but only under very sort of special circumstances. So I think when we hear from the next speaker, you'll hear about the situation in Scandinavia. Obviously, again, they have a lot of hydroelectric power, so it makes it more conducive to sort of fast tracking this evolution. In a lot of the rest of the world, it's a much more difficult road.
Jeremy, thank you very much. We're now switching to our next presentation, and there'll be a share screen switch with your contact information as jeremy.jones@cixllc.com. At this point, Michelle, would you take it over and please present our presenter, Dennis Hennessy?
Thanks, Charlie. Good morning, good afternoon, good evening to some. I am pleased to present Dennis Hennessy, not only a wonderful person in the steel industry, but a good colleague of mine who I had the great opportunity to work with here at Big River Steel for almost 10 years. And he is now head of steel for Stegra in Sweden, formerly the VP of steel for H2 Green Steel. So a little name change there. To honor their Swedish heritage. Dennis studied chemical engineering at the University of Toronto and continued his education at McMaster University. So another good Canadian like Jeremy. And his previous experience has been at Stelco Steel of Canada, at 2 of their facilities, Lake Erie Works and also the Hilton Works. Also Severstal, now SDI Columbus, Mississippi. And again, Big River Steel, which is now part of the U.S. Steel company. Dennis has worked in full gamut here, melting, casting, rolling, let's see, did I say galvanizing, technical service, and he's very well known for product development, engineering, and now construction of this new facility. So thank you again for presenting to the team here and looking forward to the presentation. Turning it over now.
Hey, Michelle, thank you. Thanks, everyone. Let me share my screen here. Let me just, there we go. We should have a screen. Let me know if you can see that. Again, I appreciate Michelle for letting me the chance to talk, and Jeremy, that was great as always. So as always, super good, and the people appreciate your time. So we get this. Come on, screen. There it is, H2 Green Steel, Stegra. Slides are still switching over. So again, Dennis Hennessy, I'm the steel guy in the company, and I have a chance to talk to you a little bit about what we're doing, the people we're doing it with, and how we're doing it. So I love that. We do try and position ourselves a little bit differently. My screen may move around. I'm just in a small conference room, so forgive me. What we're trying to build is the first of the new, not the last of the old. We do have a significant customer demand. Given the choice, our banks would probably sell all of our product. Luckily, we have a great relationship with sales. We have a phase 2 planned. So with that, we are building. We're in the middle of I live up in Buda now, about 3 kilometers from the plant. Steel is up in the air, equipment's being delivered on site, so it's all coming together. And why would you build a new steel mill is always the question, and you have to have a value proposition to justify the capital and the customer interest. Luckily, we have both. They've both been great to us in every aspect of what we're doing. I'm just trying to shrink my screen. Again, I apologize. There we go. And we're trying to make sure we're always going to be a leader. When you build a steel mill, it's about needs versus wants. There's lots of other opportunities for carbon reduction after our initial stage one or phase one that we plan to utilize going ahead. So phase two would be another EAF caster taking us to around 5 million tons. But we also know we can lean down our carbon to continuously stay ahead of our competition. Examples would be in our acid regen plant. Right now, it's heated with natural gas. We've looked at flue gas from the DRI tower, and/or the burners are already set up for hydrogen. Biocarbon for injection in the furnace, syngas instead of natural gas. Other sources of electric heating in our factories is being considered. So we're going to continue to lean down. And again, a lot of the notes that Jeremy made about adding fluxes and limes. A lot of our suppliers have low carbon solutions, and we're working with each of them. So first new steel company in Europe in 50 years. They've built, there's a lot of great companies in Europe. They have a lot of great assets, galv lines, etc. But our strategic advantage, as Jeremy alluded to, is and my old boss said you need three things to make it work: power, power, power. Up in northern Scandinavia, we sit on terawatts of green hydropower. It's the value proposition that lets us do what we do. After power comes location, and that's the second part of building the mill where we did build it. All the way across the whole plant, we do have switched to a more green way of processing our materials. Our galvanized line is all electric. We know there's mills currently being built. They'll use natural gas, and they will run for the next 20 years. They'll run 24/7 to keep that furnace hot. You're not going to rebuild a galv line in the next 20 years to switch to electric. You'd probably just go build a brand new galv line. The area that we're building is, I'll say, politically supportive. The players in the market are politically supportive. They're also our investors. It is automotive, which is one of the big drivers, but we're also seeing huge interest in customers from the construction industry and obviously the white good industry, etc. So the Buden plant overview up front, you can see the electrolyzer that's 700 megawatts, our DRI tower, it's 400 megawatts, and then the balance of plant is 1.2 terawatts. 300 hectares of land. You can see we're located right beside the national grid. We have direct rail access. Port Lulia is about 30-minute car ride away, and we're just trying to hire the best and brightest to come in and join us to help us get this project over the line. When we look at this and we talk to investors and suppliers, each of these technologies by themselves is not new. I think that's typically, as engineers, our job is to assemble different pieces together and make them work in a different way. Electrolyzers, they've been around forever. The size of our electrolyzers is probably one of the world's biggest, not the biggest, but up there. TK Nucera is our partner in that. DRI towers, again, they have a great history. They're mostly hydrogen with some nitrogen. How you form that hydrogen is the key. Medrex is our technology provider. We have performance guarantees, etc. Hot feeding from a DRI to an EAF is not new. It's done around the world. Mini mills, again, not new. We're all familiar with them. Nexus, we have the second generation of their Nexus plant. Electric heating, galv lines, batch anneal. We've used this, bright anneal. All that technology has been around for quite a while. So sometimes the people outside of our industry, we just say it's like an iPhone. There's always been computer chips. There's always been programming. There's always been cell phones. But, that guy put it together in a better package. We kind of compare ourselves to that. It's a better package of existing technologies. Some of them scaled up different than others. But every time you build a steel mill, you look for an opportunity to make those improvements from the past. And how we compare, there's definitely advantages. We aren't looking to compete against 50-year-old mills. Because we're putting all this capital into this. Our hydro, wind, and solar is lets us do what we do and reduce our emissions, recognizing typically Oil, nuclear gas is how most mills do run. We do bring in LNG, full disclosure, we're not a zero carbon mill. We don't pretend to be a zero carbon mill. We don't have a gas line that feeds the mill. We do truck it in. Again, other mills typically have a 24-inch OD gas line that, fuels the mill continuously. Heating oil, tunnel furnace, batch anneal, all electric. Our primary mode of transport is electric train to the port. And from there, we put on barges and we ship it down to Central Europe. We don't have the historical legacy. We have a unified global platform that we've kind of put in place early on. Having worked in older mills and even newer mills, trying to make that work is difficult. It's never easy. How do you grab all the data? And then, the problem what to do when you get it, how can we kind of use it in a useful way to get some value out of it? So every time we do it, we get a little bit better at it. And again, here's no exception. So what we do, basically what we talked about, hydrogen production, because we do have this green, low cost electricity. It lets us drive our electrolyzers and our DRI reactor. And even with an electric arc furnace, you still need that. We do bring in scrap from external. There is less, it's not as big a commodity up in the Nordics. We do import from other places. It is closed loop. We do have agreements with our customers. When we sell steel, we get back their scrap. So coil's out, scrap in. It's a good relationship. To all the points mentioned earlier about residuals, we do make our own DRI. We generate it on site. Were there to be a hydrogen pipeline, we would more than likely participate. Our goal is to participate in any front that lowers CO2 emissions. So whether it be concrete, other heavy industries, anywhere we can support, be involved, or be a player in that field, we are interested in doing that. And the net result when we're done with all this is a 95% lower carbon footprint. And even from the beginning, there's 50 projects we could probably start doing to reduce our carbon footprint even more. But it's always a cost thing to make a product so expensive no one can afford it. Doesn't make sense. First, we need to just get up and make a coil. That's kind of where it all starts. Again, picture of our electrolyzer. We're going to make 100,000 tons of hydrogen, 700 megawatts. We've pre-sold actually well over 1 million tons. These are all public records. All sorts of groups, suppliers, automotive, they've all stepped up, supported us. We have 7 years of contracts with these people that we use to go to the banks and provide collateral. That's how you build these projects. And again, phase 2, we want to ramp up to 5 million tons, 30 EAF, another set of LMFs, another RH, another caster, added tunnel furnace, third coiler. And then we look at some downstream processing, where else we can do it. Growth projects, we're interested in Portugal, being a DRI player there. Brazil, it's made of iron, has great hydropower resources. Texas, it's well known as a place where people make DRI now. Quebec, as said earlier, the hydro resources up there is kind of second to none. It's able to be gained, within 5 years, we could bring on, hundreds of megawatts of power, which is what you need to drive these sorts of projects, power, power, power. What's it cost? Cost $6.5 billion. The joke was steel mills used to be made by millionaires. Now they're done by billionaires. And the site's changed significantly since this picture was taken. It's covered in snow, but B, foundations are in all the way through the steel shops. We got the DRI tower going up. The footprint for the hydrogen is going up. So it continues. 2.1 in equity. These are all the people that put up hard cash to support us. They've been there from the beginning. And banks, we always go hand in hand with banks, 4.2 billion. And we had a $250 million grant from the EU, European Commission. Typically, countries by themselves, at least on this side of the water, have a lower tendency to support directly. What it avoids is big countries supporting their processes over little countries, but this came from the EU for innovation. We talked about our growth projects, our suppliers. Obviously, SMS is doing the steel side. We have some other smaller vendors supporting us as well, all equally important. Thyssen, Nocera, again, they spun that off. And that's kind of how we're building our plant. But I will jump down to some questions while I got some time, if that's all right. And I may even stop sharing. There we go. So if you want, I can take some questions and answers, or how do you want to talk about that? Michelle, do you want to control the questions, or should we jump into it? Oh, Peter asked, what's the price for electricity required to make this business model work? I'll say our cost of electricity is low. I would take it as on par with the lowest what you probably see in the US and Canada. There is a sensitivity around that. And then you look at how many kilograms of hydrogen you need to reduce a ton of iron. So, it's going to be between 45 and 65, 61, and what that means and how you scale it. So for the business model to work, it's not only the price for electricity, big part of it, it's raw materials, it's what you're trying to make. So hopefully I answered that question. Question was LNG used for carbonization, the DRI? Yes, absolutely. That's where the majority of the LNG is being used. We produce a DRI of 1.3% versus a probably typical 3.4 to 4% higher standard DRI type unit, and that feeds directly into our EAF. But we also sell cold HBI on the market. We do have pelletizers that we do send out, and we have takeoff agreements as well. Just trying to answer the next one. Where would you get iron ore pellet feed? We currently have 2 suppliers, one from Brazil, one from Canada. We're working on the 3rd one from up the road in Sweden. Currently, that's trying to be resolved as a supplier to us. So ideally, we'd rather have someone who's close to us versus having to put it on a boat and ship it across the water. But that's currently our way of getting the pellet feed. So can we compete without the green premium? Yes. Nice thing about Europe is it is a well-developed market. They typically make high commodity products. There is a cost of having green steel, and we do charge for that. We won't say the number, but if you were to put a mini mill and put it in and go head to head with some of the existing mills, I think we'd find it similar to what we see in North America, in that we are as good or better in being able to produce the products and make money. So we will start up this mill without a hot DRI at first, probably 6 months ahead of time. We will bring in pig or HBI to run our mill and get it started. And from there, we'll do the product development ramp up, and then we will onboard the DRI as soon as the tower is completed, and use that and further drop our green footprint. But even as a mini mill, we'll have a significantly lower carbon footprint than our BOF competitors, which is great.
Dennis,
Go
do you
ahead, sir.
mind sending the rest of the questions to individual
Sure.
after the presentation?
Yeah, and I'm done the presentation, so I'll
Excellent.
close it up.
Very good. Michelle, Kyle, Jeremy, Dennis, thank you very much for your addition to this webinar series and your insight with today's material. If my screen is showing, we've got contact information for Dennis Hennessy at dennis.hennessy@stegra.com.
Thank you.
You're welcome.
Thanks,
Dennis,
everyone.
And our complete population of attendees. We have a series of webinars. There's another one coming up on the 4th of December, created by our Middle East and North Africa chapter, and it has at least 5 contributors. That is time to be able to assist that part of the world, but it's also, like this webinar, available. We have a complete list of these webinars on decarbonization at this webpage, and if you can see my cursor, please go to this part. We'll take you to a running stream of about 12 decarbonization webinars that have been put on by AIST over the last 4 to 5 years. We also want to remind people that there's a resource library that has over 10,000 available papers, technical resources at your disposal as a member. And The in-person conferences that we plan in January, February, and now March are coming quickly at the beginning of the new year. Additional information is at the calendar. If you just want to focus on the in-person training, then reduce it down to just technology. Of course, everyone, we're going to remind folks that the 5th through the 8th of May, AIST Tech occurs in the city this year is Nashville, Tennessee, and we hope to see you there. Thank you for your time. Thank you for attending, and thank you for your questions. Again, thank you all, moderators and presenters, for your material today. Have a good day.